Welcome, dear friends. Am I audible? Okay, thank you. Thank you, dear all. Let me share the screen. The plan is to solve few numericals on Exergy and to make sure that you have internalized the concepts. Okay, that is the plan today. So take down one numerical. Write down one numerical. The question is, the system at 400 Kelvin, I'm dictating it and I would also be writing on the board. A system which is at 400 Kelvin receives 150 kilojoules per second of heat. The question is, I'm writing now on the board. A system at 400 Kelvin receives 150 kilojoules per second of heat from the source which is at 1200 Kelvin. The atmospheric temperature is 300 Kelvin. So we would be assuming that the dead state temperature is equal to the atmospheric temperature. The atmospheric temperature is 300 Kelvin. And we need to assume that the temperatures of the system and the source, they remain constant during the heat transfer. We assume that the temperature of the source and the system, they remain constant during the heat transfer phenomena. Okay. So what you are required to find is, you are required to find the net change in entropy. That is entropy change of the universe or entropy generation. That is to be calculated. Second, you need to calculate the available energy of the source and of the system, of the source and system, and you need to calculate the decrease in available energy, decrease in available energy, decrease in available energy. Okay. And fourth is you need to represent this process on a temperature entropy. Represent this process on the temperature entropy diagram. Okay, so this is similar to what we had solved yesterday. Okay, I'm taking this in order to ensure that you understand the concept. Okay. So let me ask you one question, whether the heat transfer is reversible or irreversible. There is no heat loss. Okay, there is no heat loss. There is no heat loss. So I'm asking you whether the heat transfer is reversible or irreversible. So Gargi has answered. Any others? Whether the heat transfer is reversible or irreversible. Tejas, Kamlesh, what is the answer? Whether the heat transfer is reversible or irreversible. Gargi has answered it correctly. Tanaya has answered it. Ganesh, yes. Tejas has got it wrong. Tejas Khatolkar. We have got it wrong. Kamlesh, Neha are correct. Omkar is correct. Anish is wrong. Anish Patil, you are wrong. There is no heat loss, whether the heat transfer is reversible or irreversible. Only few students have answered. What about others? See, we need not confuse the heat loss with the reversibility of the heat transfer. Okay, even if the heat loss is zero, the heat transfer could be irreversible. And when is the heat transfer irreversible? The heat transfer is irreversible if the temperature difference between the source and the system is finite. So in this case, in this numerical, it is given that the temperature difference is 800 Kelvin, 1200 Kelvin minus 400 Kelvin. Okay, so the temperature difference is finite. 1200 minus 400 is 800 Kelvin, which is substantial number. Hence, this delta T being appreciable, the heat transfer is an irreversible heat transfer. Anish, is this understood? Tejas and Anish, whether you understood this, why the heat transfer is irreversible? Tejas, Anish. Okay, thank you, Anish. So now let us solve this problem. Okay, so first thing is we need to calculate. They are asked us to calculate the entropy change. Okay, so the first find the what will happen. Let me ask you another question. What will happen to the entropy of the source, whether it will increase or decrease? Let me ask you this question. What will happen to the entropy of the source, whether it will increase or decrease, and why? What will happen to the entropy of the source? What happens to the entropy of the source? I'm waiting for your answer. I'm not seeing your answers coming. Okay, Gargi has answered. No. Gargi, don't relate it with available energy. Aditya has answered it correctly. Gargi, don't relate it with available energy. Entropy is an independent concept. Okay. Aditya has answered it correctly. Gargi has also answered it. Saurabh, you are wrong. Question is, what happens to the entropy of the source? Saurabh Bakre, you are wrong. So let me just show you the diagram. Okay, let me show you the figure so that you would appreciate this better. Okay. So let us say this is a source. Let us say this is a source, and what is the temperature? The source temperature is 1200 Kelvin. 1200 Kelvin. Okay. And we assume that the temperature, because it is an infinite reservoir, because we are assuming this to be an infinite reservoir of heat, infinite reservoir of energy, the temperature won't change, even if the heat is lost. So heat is given by the source. So along with the heat flows the entropy. Along with heat flows the entropy. Okay, flows the entropy. It means that the entropy of this means that entropy of the source would decrease. Entropy of source would decrease because it is losing the heat. Entropy of source will decrease because it is losing the heat. Okay, the source is losing the heat, right? So calculate that entropy of the source. How to calculate the entropy of the source? So you know that entropy change, ds delta S, sorry, is equal to of the source is integral of del Q by T, because T is constant, so this becomes Q by T, and because the heat is lost, it is negative. Okay, so the entropy so change of the source will decrease. So you calculate and tell me the answer. How much is that? How much is that value? Gargi, you are right. Others, Siddhi is right. Note that the heat transfer is 150. Tejas, you just check your calculation stages. So it is equal to minus 150 upon 1200. 1200 minus 150 upon 1200. Okay. So the answer is, what would be the unit of that? Most of you have got the answer. What would be the unit of that? Tell me the unit also. What would be the unit of this? Neha, what would be the unit? Tanaya has got it right. So yeah, Tanaya, yeah, pages. Somebody has got it right. Gauri has got it right. Yes, not Tanaya. Gauri has got it right. Look at the units of heat. This unit is kilojoules per second, and this unit is Kelvin. So it is kilojoules per second Kelvin. Kilojoules per second Kelvin would be the unit. Kilojoules, no Neha. Look at my unit. It is kilojoules per second Kelvin. Okay. It is kilojoules per second Kelvin. Okay. Look at the unit of heat transfer. It is the rate of heat transfer, not simply heat. Right? Okay. Yeah, thanks. Gauri, yeah. Ganesh, just take your answer. Ganesh, Gauri has got it right. Gargi, you also check your answer. Tejas, you also need to check the answer. So it is kilojoules per second Kelvin. Okay. and it would be a negative value. It would be negative value. Now you calculate the entropy change of the system. Now you calculate the entropy change of the system. Okay. So let me draw it again. So now what happens is that this heat without any heat loss, this heat without any heat loss, this heat is 150 kilojoules per second. What will happen to the entropy of the system? What will happen to the entropy of the system? So yeah, correct. Entropy of the system would increase, right, Ganesh? Entropy of the system would increase, right? And calculate that. It is very simple calculation. Okay. Because the temperature is constant. If the temperature was not constant, the calculation would have been difficult. But we are assuming that the temperature of the system also remains constant, irrespective of the heat transfer. Okay. So hence your calculation becomes simple. It becomes plus Q by T. It becomes plus Q by T. And plus Q is plus 150. And now T is the system temperature. What is the temperature of the system? It is 400 Kelvin. It is 400 Kelvin. Okay, so 150 upon 400. Yeah, you are right. So it becomes plus 0.375 kilojoules per second Kelvin. Kilojoules per second Kelvin. Okay, I hope this is clear to you, right? Most of you have got this answer right, right? So this is, now you need to figure out what is the entropy generation, okay, or the total entropy change, entropy generation or total entropy change in this transaction, in this heat transfer, the total entropy change. What would be the total entropy change? Roshan, you are right. Total entropy change, Siddhil, you have got it wrong. Total entropy change, Siddhil. Just add the two. You need to just add the two, nothing else, Siddhil. So obviously, when you add the two, it would be, Gargi, it is wrong. If you add the two, Tanaya is right, Tejas is right, Neha is right. Gargi, just take your answer. Deepalakshmi is right. Aditya is right. Siddhil, no, Siddhil, what you are doing? Siddhil, delta S of total, okay, delta S total would be delta S of the source plus delta S of the system. Okay, delta S of the source is minus 0.125 and delta S of the system is plus 0.375, which is but very obvious 0.25. The unit remains the same. Unit remains the same. Unit remains the same. Acha. I guess you people, Siddhil, you are doing some calculations which are different. You are calculating decrease in available energy or something like that, I guess. Okay. The change in entropy is 0.25. The total change in entropy. What does this mean? Your delta S total is 0.25. So what is the meaning of this? What is the meaning that you are getting delta S total is 0.25? Can anybody tell me? What does that indicate? That delta S total is 0.25. Madhuri Shinde, what does this mean? You are getting delta S total as 0.25 kilojoules per second Kelvin. Okay, so what is the meaning of this? Siddhil, Madhuri, Deepalakshmi, Omkar, Gautami. Yeah, correct. Gautami is right. No, Tejas is not right. The Gautami is right when she is saying that the entropy generation is because of irreversible heat transfer. Okay. The entropy generation is because of irreversible heat transfer. Okay. Thanks, Gautami. So please note that we are getting this value as positive 0.25 and not 0, because the entropy, because the heat transfer is irreversible heat transfer. If the heat transfer was a reversible heat transfer, the delta S total would have been 0. Please note, if the heat transfer would have been a reversible heat transfer, you would have got the delta S total is equal to 0. What if you had got delta S total as negative? What if you had got delta S total as negative? Any answers? What if you had got delta S total as negative? No answers? Yeah, Gautami is right. So, yeah, Gautami, it means no. Garge is not the case. Gautami is right. If you would have said that the heat transfer was impossible, this heat transfer was impossible. Okay. So, you need to understand that the value of entropy change of the universe. This is basically delta S total means what? It is basically the change in entropy of the universe, or it is, in other words, it's the entropy generation, or it is delta S total. It indicates that it is always positive when the process is irreversible, and it can never be negative. If it is negative, you can say that that process is not possible. Straight away, you can say from the second law that this process is impossible. Okay. So, in a way, the beauty of this is we are quantifying the irreversibility. Okay, we are not simply saying that qualitative, we are not simply saying that it is irreversible. We are now quantifying the irreversibility, and that quantification is, in this case, it is 0.25. It is 0.25. Okay. Now, the next part of the problem, we need to now calculate the available energy of the source. We have calculated the net change in entropy. Okay, and we have got it positive, which means that it is a irreversible process. Okay, now you need to calculate the available energy of the source. Available energy of the source. So let me draw this on the TS diagram. Available energy of the source. So what is the source temperature? You need to show it on the TS diagram. So for showing available energy of the source, you need to know the source temperature. That is, in this case, it is 1200 Kelvin. And what is the other temperature you must know? What is the other temperature you must know for showing the availability? One is the source temperature, and what is the other temperature we must know for showing the availability? No, Gautami, Ariki, you are wrong. Yeah, correct. Tejas is correct. We need to know the dead state temperature. We need to know the dead state temperature, that is ambient temperature, which is 300 Kelvin. 300 Kelvin. If you are referring to, just note, I am telling a very important point. If you are referring to textbooks, okay, which are published by authors, like some Technova or some TechMax, like that, you'll find that in many books, because their concepts are not clear, they make this mistake in calculation of available energy. Okay, so please note that when you are referring to some textbooks, don't refer to their solutions, okay, especially for this chapter, because I had referred to some books for getting the questions, and I have found that the authors have made a very fundamental mistake, because they have not grasped the idea of available energy. Okay, so you need to be very sure that when you are talking about available energy, we need to be talking about the dead state temperature and the source temperature if you are calculating the available energy of the source. Okay, and how do we represent that available energy of the source? So for representing this, we need to consider the heat transfer process. Now, when there is a heat transfer process, obviously there would be an increase in the entropy from some value 1 to 2. 1 to 2. Okay, S1 to S2. Okay, and then we need to see that this heat transfer is a reversible heat transfer to a Carnot engine, and the Carnot engine rejects the heat at the dead state temperature, not at the system temperature. Mind that. The Carnot engine rejects the heat at the dead state temperature, not at the system temperature. So this area, okay, this area of the rectangle, is the available energy. This area of the rectangle is the available energy. So what I represented is the available energy. And how do you calculate this area? So this is nothing but W max, okay, of a Carnot engine. This is nothing but W max of a Carnot engine operating between the source temperature and the dead state temperature. Okay. So available energy of the source. So I have represented on this diagram the available energy of the source, which is the area of the rectangle. Let us say A, B, C, D. Area of the rectangle A, B, C, D. And how do you calculate that? So available energy of the source, is equal to 1 minus T naught by T into Q. Okay. So the heat transfer is given to us as, how much is the value? 150 kilojoules per second. So this is 150 kilojoules per second. 150 kilojoules per second. Okay. So I'll just rewrite this expression because now what I have is directly the entropy change value. Okay. So I can use the entropy change of the system. Sorry, the source. Okay. So how much is the value of Q? How much is the value of Q? The value of Q is 150 kilojoules per second minus the dead state temperature, which is 300 into what is the delta S of the source? Delta S of the source we are found out as minus 0.125. Okay, it is 0.125. Okay, so this becomes 150 kilojoules per second, and this becomes, I guess this is how much? 125. Just calculate. You can also calculate simultaneously. So it is 37.5. 37.5. Okay, and then this comes as so this is 112. Yeah, correct. Margi, you are right. It is 112.5 kilojoules per second is the available energy. Is the available energy of the source. Is the available energy of the source. Okay. Though it is not asked. Okay. What is the unavailable energy now? Though it is not asked. What is the unavailable energy? What is the unavailable energy? Raju, you are right. Raju has calculated it correctly. What is the unavailable energy, Raju, now? Tanay has also calculated. Yeah, correct. So unavailable energy would be obviously Q minus. So it is very simple. Unavailable energy of the source. Unavailable energy of the source would be Q minus. Unavailable energy of the source would be Q minus available energy of the source. Okay, of the source. That is Q is 150 minus 112.5, and this is 37.5 kilojoules per second. Okay, and can we show that unavailable energy on the TS diagram? We can. Okay, we can show the unavailable energy on the TS diagram, which is the area under C to D. Okay, so this area under C to D, if I call this as some E and F, so area C D, E, F. Okay, C, D, E, F is the unavailable energy. Is the unavailable energy. Okay, right? And what is the area under A to B? The area under A to B is the heat transfer. Okay, so heat transfer is available energy plus unavailable energy. Okay, so this is the first part of the question. Now, what was asked? It was also asked the available energy of the system. Okay, some students have already calculated it, but I'm going a bit slow in order that all the students they understand. So I know that some students are very quick in responding, but in spite of that, I am going a bit slow. Okay, so I am now calculating the available energy of the system Okay, so this is source temperature 1200 Kelvin, but I am not bothered about source temperature now. I am bothered about the system temperature, which is 400 Kelvin, and I am bothered about the dead state temperature, which is 300 Kelvin. Okay, so the available energy would be some, let us say, I, J, K, L. Okay, so this would be the available energy of the system. And this IJKL, let us say this is M and N. So this portion L, M, N, K is the unavailable energy part of the system. Okay, of the system. So again, calculating the available energy of the system, 1 minus P naught by P dash, let us say now, I'll just use P dash into Q. There is no heat loss, so Q remains the same. So Q minus P naught, Q by P dash. Okay. So Q minus T naught, this is delta S dash, which is nothing but the delta S of the system now. Delta S of the system. Okay. So now you can put these values. There is one more expression which you can remember. You know what is Q? Q is actually, what is Q? Q is actually T into delta S of the source. Okay. So this also you can use if you want. Any expression you use, as long as it is consistent with our concepts, okay, you will get the same answer. Okay. Now putting these values Q and P naught and delta S dash, because delta S dash we have the value as 0.375. This is 0.375. Then the dead state temperature is 300, and the Q value we already know. It is what? It is 150 kilojoules per second. Okay, 150 kilojoules per second. So substituting these values, you'll get, I guess, 37.5. 37.5 is the entropy. Sorry, it is the available energy of the system. Okay. Now, if you look at the available energy of the source, was 112.5, and now it has decreased to what? Sorry, it has decreased to 37.5. Okay, so the decrease in available energy, which is the same as increase in unavailable energy, decrease in available energy is available energy of the source minus available energy of the system. Okay, so this comes as, what was that? 112.5 minus 37.5. Okay, so this is 75 kilojoules per second. Okay, 75 kilojoules per second. I hope you understood this. This is understood. Gauri is right. Gargi is right in calculation. So the decrease in available energy is 75. Decrease in available energy is 75. Any doubt in this? Anybody who has not understood anything from this? See, these problems are very simple. And even if you don't understand any concepts of available energy, unavailable energy, and whatever, you can simply mug up the formulas and solve these problems. Okay, just go blank into the question paper, put the values, use some formulas, and get the answer. But if you appreciate the concepts, then you would be in a position to enjoy that problem. Okay, so if you want to enjoy the problem, so I am spending so much time because I want you to enjoy the problem. But even if you don't want to give your much headache to your brains, okay, if you don't want to take pens, then also solving these problems is pretty simple. Okay, pretty simple. So mathematically speaking, these problems involve very few formulas. Okay, and these problems are very quick. We can quickly solve these problems and score marks. Okay, what is difficult part is, and nobody is going to ask you in the exams that part, is to appreciate the concepts behind these numbers. Okay, so that is really fun. So if you want to appreciate the concepts behind these numbers, okay, and if you want to understand really what is happening to the quality of the energy, okay, then whatever discussion we are having, that is more relevant. Okay, otherwise you can simply solve it mechanically also, okay, and score the marks. I hope that is clear to you now. Okay, this is just to make sure that you are not terrified by this chapter on Exergy, okay, and you don't put it in option. Okay, so that is the reason why I have mentioned this. Otherwise, I would not have mentioned this also. Okay. Hopefully, this is clear. Any doubts regarding this? Anybody has any issues with this that you are not followed or something? Okay. So let me move to another problem. Now I'm just going to discuss this problem, and maybe I will be solving it in the next class. Uh, this is a very interesting problem and a very practical one also. We have been studying boilers in the class now. We have started with the boilers also simultaneously. So you know that the boilers, in the boilers we generate steam. Okay, in the boilers we generate steam. Okay, and we have a separate chapter on properties of steam later. But for the time being, just assume that that there is a boiler. Okay, what's happening? Okay. Let us say that there is a boiler, and this boiler, okay, is heated. The water in the boiler is heated, and it is boiled actually. Okay, it is boiled at a constant temperature of, say, some temperature, constant temperature. Okay, at 250 degrees centigrade, let's say, at a constant temperature of 250 degrees centigrade. And for heating this, let us say that you are using a furnace which gives you the flue gases, okay, or you are using some heat exchanger which gives the flue gases, means products of combustion. Products of combustion. Products of combustion. You know that hot gases which are coming from the furnace, they would be at some higher temperature. Let us say that they are at some high temperature of 1100 degrees centigrade. Okay, 1100 degrees centigrade, and then they would emerge out, okay, at some lower temperature. Let us say that they emerge out at some 500 degrees centigrade. 500 degrees centigrade. So now in this case, what is the source of heat? Let me ask you this question. What is the source of heat? In this diagram, what is the source of heat? Gauri, Gargi, Ganesh, anybody? What is the source of heat in this problem? And whether this source is a finite source or infinite source. Kunal, Siddhil, Tanaya, Tejas, Deepalakshmi, Raju, anybody, okay, from your side. Ganesh. Ganesh is saying that combustion is the source of it. Okay. Whether it is a finite source or infinite source. See, what I am saying is that the combustion gases, okay, they are let into the boiler at some 1100 degrees centigrade, and they are emerging out at 527 degrees centigrade. Okay. So you see that the source is a finite source. Okay. Why it is a finite source? Because the temperature of the source is decreasing. Okay, the temperature of the source is decreasing. Are you getting on? Temperature of the source would decrease. So if I want to represent this on the temperature entropy diagram, how would that look? If I want to represent what happens to the temperature and entropy of the gases, if I want to represent what happens to the temperature of the gases and the entropy of the gases as they transfer the heat to the boiler, So how can I represent that? What will happen to the temperature of the gases? As is shown, the temperature of the gases would reduce. Temperature of the gases would reduce. What would happen to the entropy? What would happen to the entropy of the gases? No answers? So the entropy would also reduce. Okay. It means that, yeah, correct. Who has answered this? Let me see. Entropy has reduced. Somebody has answered this. Okay, Tanaya has answered this, correct. The temperature would decrease and entropy would also decrease. So if I want to represent this on a temperature entropy diagram, it would look somewhat like this. Okay, it would look somewhat like this. So it was earlier the temperature was say 1100, and now it is 500 degrees centigrade. 500 degrees centigrade. Okay, correct, right? And there was some entropy. Let us say this is 1, this is 2 process. Well, state is 1, this is state 1, that is entry of the flue gases, and state 2 is the exit of the flue gas. Okay, so the entropy at state 1 would be S1 and entropy at state 2 would be S2. This is the temperature entropy diagram. I hope it is understood. Okay, now what is the, can I show the heat transfer which has happened on the temperature entropy diagram? Can I show the heat transfer which has happened as the flue gases reject the heat to the boiler? Okay, supply the heat to the boiler. As they supply the heat to the boiler, can I show this heat transfer on a temperature entropy diagram? Yes or no, and how? I hope the question is clear to you. Let me ask you the question. Can I show the heat which is being transferred by the flue gases on the temperature entropy diagram? And how? If yes, how? If no, why not? Can I show the heat transfer by the flue gases to the boiler. All right, Sharvari. Gautam is saying yes. How we can show? It is Gautam. How we can show? Army, how we can show that? We can show it by the area under the line 1 to 2. The area under the line, Gautami and Gargi, the area under the line 1 to 2, the area under the line 1 to 2 is this is the heat transferred by the flue gases. Heat transferred by the flue gases, right? So the area under 1 to 2, this area, if I show it by hatched lines, this area is the heat which is transferred by the flue gases. Okay, and how do we calculate that heat transfer? How do we calculate the heat transferred by the flue gases? Which expression we can use for that? Which formula, which expression can we use for calculating the heat transferred by the flue gases to the boiler? No, Gargi, that is not correct. Which expression, whether it is a sensible heat transfer or latent heat transfer? Yeah, Tanaya, you are right. Tanaya is right. It is a sensible heat transfer. So I can calculate the heat which is lost by the flue gases or heat which is transferred by the flue gases. Okay, heat which is transferred by the flue gases to the water inside the boiler for boiling that water by the expression mass of flue gases, specific heat of flue gases, and in this case, for example, in this problem, it would be 1100 minus 500 delta T. In this problem, it is 1100 minus 500, or generically speaking, it is mCp delta T. Thank you, Tanaya. Okay, so the heat which is lost by the flue gases can be represented as the area under the curve 1 to 2. Okay, on a temperature entropy diagram, and it can be calculated as mCp delta T. The question is, what about its exergy? How do you calculate its exergy? How do I calculate its exergy? Exergy of the flue gases. This is the heat of the flue gases. So how do I calculate the exergy of the flue gases? Or available energy of the flue gases? So without going into the proof, let me tell you that this can be calculated as, and I'll do this later, QFG minus T naught delta S, where T naught is the dead state temperature and this is delta S. Delta S means it is QFG minus T naught. Using my notations, it would be S1 minus S2. Yeah, correct. Right? So the available energy of the flue gases can be calculated as QFG, that is the heat which is lost by the flue gases, minus T naught delta S, minus T naught delta S. Okay, what would happen to the entropy of the flue gases, whether it will increase or decrease? What will happen to the entropy of the flue gases, whether it will increase or decrease? The entropy of the flue gases would not increase, Gargi, it would decrease. It would decrease because I'm talking about delta S. I'm talking about delta S. Okay, so entropy would decrease because the heat is being lost. Heat is being lost by the flue gases. Okay, Siddhil is right. Heat is lost by the flue gases. So the entropy of the flue gases would decrease. Okay, decrease, right? Okay. Now, suppose this heat is going to the boiler, okay, which is boiling the water at 250 degrees centigrade. Okay, so how do I represent that process on a temperature entropy diagram? What would happen to the temperature of the water in the boiler? What would happen to the temperature of the water in the boiler? Garge is saying it is increasing, but I am saying that it is boiling. So in the boiling, you know that boiling phenomena, the temperature remains constant. Okay. When it is boiling phenomena, if it's not sensible heating, if it's only boiling phenomena, then the temperature would remain constant. Okay. And what would be that temperature? So let me use another pen for that. The temperature, if I want to show that temperature of the boiling water on a temperature entropy diagram. So I'm using a red pen now. So this would be, let us say this is your temperature, which is 250 degrees centigrade. Okay, 250 degree centigrade. Okay, so this is the temperature which is 250 degrees centigrade. Right. Now, what would be now your system is what? In this case, what is the system? The source is the flue gases. Source is the flue gases. What is the system in this case? Yeah, boiler. Water which is boiling in the boiler is the system. Okay. Water which is boiling in the boiler is the system. Okay. So what would be the entropy change of the system? What would be the entropy change of the system? Whether it would be again delta S, which is S1 minus S2. Again, in this case, whether the entropy change would be S1 minus S2, or it would be less, or it would be more. Acha. How can we represent the heat which is gained by the boiler on a temperature entropy diagram? How can we represent the heat which is gained by the water in the boiler, okay, on a temperature entropy diagram? How can we represent the heat which is gained by the water in the boiler on a temperature entropy diagram? It can be represented by the area under the temperature line to 50 degrees centigrade. It can be represented as the area under the temperature line to 50 degrees centigrade. Okay, and that area has to be equal to what? That area has to be equal to the area under 1 and 2. That area has to be equal to area under 1 and 2. And why is that so? The area under 1 and 2 and the area under 250 degree centigrade line has to be the same. Why is that so? Why should the area under 1 and 2 and the area under 250 degree centigrade line has to be the same? Any answers? Nobody has the answer? Yeah, correct. Gautam is correct. The answer is same amount of heat is transferred. There is no heat loss. If there was a heat loss, the area would have been different. There is no heat loss. Okay, so the area is the same. Okay, so we'll continue with this concept. What actually I have started is, I have started the discussion on the calculation of Exergy if we are talking about a finite source. In this case, I have taken an example of a finite source, that is a flue gases whose temperature, the source temperature, that is the flue gas temperature, is reducing because the heat is being lost by the flue gases. So it is not the case of an infinite reservoir, the source, It is a case of a finite reservoir, that is the flue gases, which is transferring the heat and simultaneously experiencing the temperature drop. Okay, so in such kind of problems, how do you calculate the exergy? Okay, that would be an interesting kind of discussion. Okay, so see you in the next class. Thanks for joining. Okay, have a good day.